Hi, welcome back. Today we're going to talk about linear regression, which is an incredibly useful, incredibly important topic. Okay, and generally you would learn about linear regression maybe in a first statistics class, and you get some statistics perspective on what linear regression is, which is very useful and very valid. But if you can understand linear regression from a linear algebraic perspective, from a geometric perspective, you'll get a much deeper understanding of what linear regression is, because you have another way of looking at it. And then when you move on to some more complicated kind of regression, or a more complicated linear regression even, your geometric knowledge will be like a mental model that will generalize easier than just trying to generalize the brute force statistical methods. Okay, so we're going to start with a really simple example that will illustrate linear regression. Okay, so the first example you learn is you have some data points. Maybe you have two variables that you're measuring. I don't know, you have the square footage of a bunch of houses, and you have the price that those houses sold for. And you want to determine the relationship between square footage and price. So what you would do is you could plot square footage on one axis and price on the other, and then try to see what the data looks like. Okay, so we of course don't want to deal with a lot of data points or a lot of crazy numbers, so we're going to do a really simple example. I'll do the one that's in the notes, 061020. And we might want to figure out what's the line that predicts the relationship between these two variables based on this data that we've collected. Okay, so problem here is find the best fit line. Okay, so the point is that almost certainly, if I give you some data like this that came from the real world, even if there's a roughly linear relationship between the variables, they're almost never going to all lie on a line, right? Because 2 points always lie on a line, but once you've added a third point, it needs to be in a very special place to lie on the line, right? So uh, because of that, that means that the problem that we'd like to solve is not solvable. So the dream is all of our points lie on a line. If that were true, it would be really easy, right? You have slope intercept form, you take any two of the points, and then you just find the line between them. Okay, but this will basically never happen. So not all your dreams can come true. That's a terrible lesson. uh, so what we'll do instead is we'll try to find the best fit line, the line that's closest to all of these points in some sense. Okay, and linear algebra will help us do this. And it turns out that our linear algebra notion will correspond exactly to the statistical notion. Okay, so let's imagine that our points did lie on a line. Okay, so suppose if they did lie on a line, what would that mean? That would mean that they would all satisfy y equals ct plus d. I want to stick with the notation in the notes, so I've done this all wrong. They would all lie on us, right? So let's call this one the t-axis and this one the s-axis. If they all lied on a line, then when you would plug them into this equation, you would always get equality, right? In other words, you would have 6 equals c plus d times 0, and you would have 1 equals c plus d times 1, and you'd have 2 equals, sorry, I've done this wrong. 0 equals c times d plus c plus d times 1, and you'd have 0 equals c plus d times 2. If they all lie on a line. Okay, but now we're getting somewhere linear algebraically because, right, so because then we could write this in terms of linear algebra as, now my variables are c and d, and the linear equations are 1, 0, 1, 1, 1, 2 equals 6, 0, 0. So if all the points lay on a single line, then this system would have a solution. That's exactly what it would mean to say that they would lie on a line. You would be able to exactly express the line in terms of a slope and an intercept, and they would satisfy this. Okay, but this system is not solvable because they don't all lie on a line. So this system's not solvable. Let's call this vector B. Let's call this matrix A. This system is not solvable because they don't all lie on a line. Well, why is this system not solvable? The reason that the system is not solvable is because B is not in the column space of A. No vector that you can multiply A by will give you B, right? This is because B is not in the column space of A. All right, so there's a whole bunch of possible, if you change B, you might get a consistent solution, right? What is the column space of A? The column space of A is the span of the columns. 1, 1, 1, 0, 1, 2. Right, so the span of the columns, the column space of A is some two-dimensional plane in R3. This is like the column space of A. And so almost all the time, if you have data like this, you get some vector B, almost all the time the vector B will not be in the column space of A, because the column space of A is a two-dimensional plane inside of a three-dimensional space. And so because of that, you wouldn't be able to solve for C and D the intercept and slope of the line that passes through all the points, right? And of course, if I added more points, if I added more data points, that would be adding more and more rows to this matrix, right? Each of these came from an equation that came from each data point, each row, which would mean that if you added more and more data, the size of your space is going up, right? We're in R3 right now because we had 3 data points. If I had 20 data points, we'd be in R20. Still, the column space of A is always going to be two-dimensional. So the chances of 20 points lying on a line is extremely slim. But we just learned that instead of solving solving ax equals b, what I could do is I could project b down to the column space. And if I project b down to the column space, that's sort of the closest thing in the column space to b. And then that system would be solvable. Right? So instead of solving this system, which is not solvable, ax equals b, we could instead solve the system ax equals the projection of b onto the column space of A. And because I projected onto the column space of A, this system will definitely have a solution. Right? Call this solution x hat. Right? For convenience, I'm going to call a lot of things different names. Let's call this projection P. And a solution to this we'll call x hat, because it solves basically an approximate equation, right? Ax equals an approximation of b. So we should remember how to solve for projections from last time, right? So how do we solve for b? So what is b? Or what is p, rather? Right, so b is 6, 0, 0. And we had some normal equations last time. So let's remember them. Where are you? Here. we should multiply by this matrix, A transpose A inverse A transpose, right? So P will be A transpose A inverse A transpose, and A here was this matrix, 1, 1, 1, 0, 1, 2. Right, so A transpose A, 1, 1, 1, 0, 1, 2 is equal to 3, 3, 3, 5, which is definitely invertible, right? Sorry, we should multiply by B here. And then you just take P equals A times A transpose A inverse times A transpose. And luckily, it's done for you in the notes to get that this is equal to 5 to negative 1. Right? Because this one is 3 by 2, this one's 2 by 2, this one is 2 by 3. Sorry, I forgot to multiply by B at the end. My bad. 6, 0, 0. This one is 3 by 1. This is 5 to negative 1. And now AX equals P does have a solution, which you could solve using Gaussian elimination, or probably more practically, your computer algebra system of choice, to find that X hat is equal to 5, negative 3. Okay, which means that, remember, this matrix was supposed to give us the intercept and the slope of our line. This means that 5 minus 3s, sorry, t, s equals 5 minus 3t, should be the best fit line. Best fit in what sense? Well, from the way that we've developed it, it's the best fit in the sense that it's the line that would solve the closest consistent system to this one, right? This leads to an inconsistent system. If we adjust the data points, right, the data points, the 6, 0, 0, the B, came from these data points. If we adjusted them so that we actually had a consistent system, it's like we would be shifting these points up and down, right? So if we shift these points up and down until they actually lie on a line, and if we shifted them in a way to get as close as possible to the vector B, such that it would have a solution, then the line that we would get would be 5 minus 3t, which is a line that looks something like, oh gosh, so 5 is like here, and it goes down 3 every time, right? So it goes like here and like here. This is the line 5 minus 3t. S equals 5 minus 3t, if you prefer. And that, in fact, does look like it will sort of pretty reasonably model the data that we have here. Okay, but notice that this is not how the best fit line is defined in statistics, right? In statistics, the best fit line is defined as something that sort of minimizes the squares of the distances from the points to the line, right? And we can actually see why if we think a little bit about projections. Okay, so let me copy and paste this over here onto a new slide. Right, and the point is that, okay, so the blue points are our original points. Let me try to erase these. The blue points are our original points. And this line goes to the points 0, 5, 1, 2, 2, negative 1. Right, notice that the y coordinates, sorry, s equals 5 minus 3t. Notice the y coordinates here give you exactly the vector 5 to negative 1. That was the vector p, which was projection onto the column space of A, B. Right, so like I said, what we're doing is we're shifting the points up or down until we get a solvable system. So we're shifting them up and down until they lie on a line, but we're sort of shifting them in a way that they're close to the original points, because the original points are represented by the vector b, which was 6, 0, 0. Those were their heights, right? Okay, now recall that b was equal to p, which was the projection onto the column space of A, plus some error term, right? Or in other words, p was equal to, or b minus p was equal to e, right? Just rearranging. Now, what does this mean? This means that this vector e, right? If I'm writing down the actual vectors here, 6, 0, 0, minus 5, 2, 1. This is 1, negative 2, negative 1. This vector e is recording, maybe I'll write it in a different color. This vector e is recording the differences between the points that we actually had and the line. Or in other words, when we shifted the points so that they lay on a line, the differences are captured by e. And when we developed this idea of projection, what we did was to project B onto the column space of A, we minimized this thing, ax minus b squared. But the minimum value ended up being the magnitude of e squared, right? Because we just rewrote this as ax minus p plus e, right? Squared. And then we use the Pythagorean theorem because ax minus p was perpendicular to e. And then you can make this part 0 because you could pick a point that was actually equal to p. So this is the minimum value. This was the thing that we're minimizing when we take a projection. But what is this? This thing is exactly like e1 squared plus e2 squared plus e3 squared. This thing is exactly 1 squared plus this is probably on my face, I'm guessing, in the recording. This thing is exactly 1 squared plus negative 2 squared plus negative 1 squared. In other words, in this process of projection, when we projected the vector b of the heights onto the column space of A, we were exactly minimizing the squares of these differences, which is how linear regression is taught in statistics. You're taught that the least squares regression line is the one that minimizes the squares of the vertical distances from the data points to the line. But it turns out that that's exactly the same thing as what we just did using linear algebra. But I think the linear algebra picture is actually a better picture. It's this picture, right? The point is that we have a system that's inconsistent, because in real life, data is almost never going to lie on a line, so we'll have an inconsistent system. But what we'll do is we'll project the data vector b, we'll try to project this vector b onto this vector A. They both come from data, right? Onto the column space of this matrix A. And then that thing is solvable. In other words, we just change the heights a little bit by projecting B onto some place where they do all lie on a line. And then that thing gives us the best fit line for linear regression. Okay, so we should write down a general algorithm in this special case, and then let me talk a little bit about, well, what if you want to do more complicated linear regression? So here's the algorithm for the least squares regression line. Okay, so the input that you have is you have a bunch of data points. So T1, B1, T2, B2, TM, BM. Right, again, you can think of square footage as your T's, and home prices as your B's, and you went and collected M different houses, right? The output of this algorithm is the line L that fits the data the best. What do I mean by the best? I mean, if you take the squares of the distances to the line, it's minimized over all possible lines. Okay, so what do? You set your vector b to be the vector of b1, b2 through bm. Right, now if there was a line s equals c plus dt through these points, through all the data points, then the following matrix would have a solution. Right, because each ti let me just write this down first before saying what I'm trying to say. You would be able to solve this for C and D such that you would get C plus T1 was B1, C plus D times T2 was B2, C plus D times Tm would be Bm. Right, so this would have a solution. In other words, this would be a consistent system. And sometimes, I guess that could happen if you have very few points, say. But if not, I mean, even if it was, if you projected, it wouldn't do any harm. So, but if the system is not consistent, sorry, let me give these things a name. This thing is called A, this thing is called B. Then project B onto the column space of A to get P is equal to the projection like this. Then solve ax equals P instead. This actually is consistent. It's always consistent. It's called the solution x hat, which will be some CD, right? It will be a vector in R2. Then S equals C plus DT is the best fit line in the sense that it minimizes the square distances between the points in the line. Okay, so maybe I should write that down. So for each I, if we take EI to be BI, that's the point that we had originally, the height that we had originally, and we subtract off the point that we get on the line, so C plus D times TI. This is the difference, the vertical distance between L and the ith data point. Right, then if we take E to be this vector of differences, then our line L minimized the square of the norm of this vector E, which is just the sums of the squares of all the differences, which is the way that you learned about it in in statistics, if you learn about it in statistics. Okay, there's even another fact, which is kind of interesting. I don't know if you see it in statistics or not, but note that 1, 1, 1, 1, 1, 1, this vector that I called the 1 vector, is in the column space of A. If we look at this matrix A, the first column is the all ones vector. Okay, and we know that E is perpendicular to the column space of A, because it's the error term, right? It's since it's the closest point, it's perpendicular to the column space, which means that these two vectors must be orthogonal. So if I take this vector and I dot it with E, this is equal to 0. What does this mean? This means that if you sum up the differences, you always get 0. That's not an obvious fact. So if we look at this picture here, or maybe it's actually better to look at this picture here, the differences were 1, -2, and 1. Right, so I actually... Wait. What did I do wrong? It's 2, -1. Sorry. Lots of mistakes here. 1, -2, and 1. That's a good sanity check, right? Did I make that mistake anywhere else? No, it actually looks correct everywhere else. Okay, so we've minimized the squares of the error terms, and also all the error terms happen to add to 0 by construction. Okay, now, in practice, of course, you might want to do much more complicated regressions than this, right? Because let's think about this house example again. House price, if you only collected square footage and house price, that's not very predictive because there's a lot more factors that go into the price of a house than just the square footage, right? There's like the age, the number of bedrooms, the number of bathrooms, the zip code, like the school district. There's all kinds of different variables that go into it, right? So in practice, of course, you might have many more variables. So what would you do? Instead of collecting a T1 and a B1, I guess I need to think about naming my vectors carefully here. Maybe you would collect x11, x12, x13, x1, and b1. Right? Maybe what I collect is like the square footage and the number of bedrooms and the number of bathrooms. And for now, let's pretend that it's all like numerical data, not categorical data. Like the median house price in the neighborhood, right? Maybe that's also predicted. Median house price in neighborhood. And B1 is still the price of the house. So now I have more variables, but I'll still go and I'll collect m different vectors like this now, right? So I do this m times, right? So now I have xm1, xm2, xmn, bm. I still want to know, is this price, how does it depend on all of these factors, right? But what you do now, instead of forming an m by 2 matrix, you form an m by n plus 1 matrix, right? So you basically will always have this all ones vector. That'll be like the y-intercept on your whatever your linear term is. And then you'll put all of these, and notice that I named these cleverly to sort of agree with matrix notation. Let me not put commas in my matrix. Right, and now instead of having a vector CD, I would have a vector maybe C0, C1, C2 down to Cn equals B1, B2, Bm. So this is usually called like a matrix X. We could still call this B, but since we've been using A, let's call this A. And again, almost certainly, this system is not consistent because the column space of A is going to be n or n plus 1 dimensional. But I probably have like 10 factors, but like 1,000 houses. So the column space of A will be a 10-dimensional subspace of R1000. But how do we draw that? We would draw it with the exact same picture. So here's R1000. I just have suppressed 997 of the dimensions. And here's A. Here's the column space of A, and this is a 10-dimensional subspace of R1000. So almost certainly our vector B is going to lie off of this plane. Well, how do I solve for the weights? I solve for the weights by projecting down to the column space of A, and then solving that equation, that will give me a solution here. Call it, it's usually called beta, but let's call it x hat because that's what we've been calling it. Right, so this will be some parameters c naught, c1, c2, c dot 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 up to cn. And what this would tell you is that the best fit linear model would be c naught plus c1 t1, or yeah, we have n factors here. S is equal to this. So if you gave me square footage and number of bedrooms and number of bathrooms, I could plug them in for these variables to predict the price of the house. And again, the picture, like if I taught you how to do this least squares regression line in terms of statistics, and I asked you to generalize now to a case where we collect 10 pieces of data on each house, I think it's really unclear how to do that from a statistical point of view. But from a linear algebraic point of view, the picture is exactly the same. It's much easier to generalize because we have this really good geometric understanding of what linear regression is, which is you are presented with some inconsistent system. You just project the vector b onto the column space of the matrix so that it is consistent. You solve that, and those give you the parameters that you're looking for. Okay, so another thing is that this is a really versatile thing. It seems kind of limited because I called it linear regression, and things aren't always going to be linear, right? But for example, like one really easy trick is it's instead of maybe giving the square footage and the price, if I want to model, oh, maybe there's like a quadratic relationship, I could actually just feed in the square root of the square footage. And a linear relationship between the square root of the square footage and the price will give you a quadratic relationship between the square foot and the price. So you can mess with what variables you input here. And then also you can use this idea for like a generalized linear model. It turns out that this is actually a lot more useful than it might at first seem. Okay, and I think we'll see some more applications in this class. If not, you'll see some more applications in other classes that you take. So there's a really good list of applications of linear regression given in the notes. So let me just read them. You could predict ice cream sales on a day given the temperature. So again, now you just record the temperature of each day, T, and the net sales, say, S, and then you plug them in and you try to see how does temperature affect the sales of ice cream. In which case you'd be able to say something like, oh, for every 1 degree the temperature goes up, our sales go up by $1,000 or whatever. Price, the second example is the one that I've been talking about. I don't know why houses are on the brain. Predict house prices based on data collected for price versus square footage. But again, you could include more variables, and it generalizes to a picture that you can still understand. Number of goals a player might score. So, yeah, so like in Moneyball, right, sabermetrics, you might have a bunch of different data on a player, and you're interested in, I don't know, predicting the player's batting average next season, right? Or, to be honest, I don't really follow baseball. 3-point percentage the next season based on a whole bunch of factors, right? I wonder how predictable that actually is. And these things you could actually feasibly do, okay? There's a really cool example, which is there's a link given in the notes to when in 2018, Washington State abolished the death penalty because they did a regression analysis, and they found that essentially if you include race as one of these variables here, and like this outcome vector somehow represents some measure of how you could even give it a 1 or a 0, whether or not they were sentenced to death or not. And you solve for the coefficients here. They found that race had like a humongous coefficient. Right? Something like that. In other words, they proved with regression analysis that the justice system in determining who to give the death penalty to was using race, right, implicitly as a very predictive variable. In other words, the system was sort of inherently racist, right? The notes say that black people were 4 times as likely to be sentenced to death as persons of other races, right? So maybe you have like a bunch of variables, right? Like whether or not someone is black, so a 1 or 0, whether or not someone is white, whether or not someone is Asian, whether or not someone is Hispanic, and then you look at what the coefficients you get here are. And if the coefficients for being black is way huger than the coefficients for the other variables, then that tells you that that has a larger effect on the outcome than the other variables. That's a right. And if that's true, then that's not a good thing because, of course, you don't want the death penalty to be whether or not someone gets the death penalty to be based on what race they are, right? So based on this regression analysis done in the Department of Sociology, the state of Washington actually abolished the death penalty because, right, the death penalty should not be that way. Okay, so again, we're not going to cover every possible application of linear regression in this class. We're going to cover a whole lot more different linear algebra things, but in other classes or in your working life, or if you take some Coursera courses or whatever, you will learn about different kinds of regression. And if you can have this geometric understanding, it will really aid you in understanding what's actually happening and why regression works. Okay, so you'll have a much clearer idea. Okay, and since I have a little time, I did want to talk about another sort of application of projection. It's kind of a cute little diversion. And this is called a pretty mathematical face. And so I'm borrowing this from Professor Thomas's notes, but the original source is chapter 10 in Math Bites. So that's where I'm going to show you some images by Tim Chartier, I'm not sure. Okay, and the question is, here's a bunch of celebrities. Is your face a linear combination of their faces? Okay, so I guess this is done for, I guess these celebrities are mostly male, but you could add more faces, of course, right? So question, is your face a linear combination of the faces of these 16 celebrities? Okay, so what do I mean by that, and how do we figure this out, right? So I can recognize some of them. Not all of them? No, maybe I could recognize all of them, actually. Even I can recognize all of them, so hopefully you can recognize them. So how do you do this? How could you even start to answer this question? Well, first we need some vectors, right? So these faces, your face I need to turn into a vector, and these faces I also need to turn into a vector before I can answer the question, is your face a linear combination of these faces? Right, and the point is that if we do this, the sort of the simplest thing, which is we take a grayscale image, right, of your face and of all these celebrities' faces, then every grayscale image looks like a bunch of pixels. And you can record how much light that pixel is emitting, right, on the grayscale, right? So each grayscale image we can represent as a matrix of values. As a matrix where each pixel is an entry, or where each entry is a pixel, with value between, say, 0 and 255. Right, so where 0 is black and 255 is white. Right, so in this case, this vector, this matrix A, let me give you the actual values. So the top left one is pretty brightish, so that one's 203. This is quite a dark pixel, which means that not very much light is coming through. That's a 9. This one's even brighter than the top left one. This one also is 217, 168, and 2 239. Okay, so I'm giving you the actual values from the book, I believe, of what these things are. Okay, so you can represent each picture by a matrix. In general, it's going to be a huge matrix, right? But what you can do is you can unroll this into a vector, right? So instead of taking, think of this as a matrix, what I can just do is I can identify it with a vector 203, 9, 246. Sorry, I'm not writing. 246, 217, 168, 239. Okay, but of course, when you take these celebrity photos, or when I take a picture of your face, these are humongous vectors. These are humongous matrices, right? So each of these, I guess, is supposed to be 600 pixels wide by 900 pixels tall. So each face can be considered as a vector in R to the 600 by 900. So this is R to the 540,000, 540,000. And then what you can do is you could take each of these 16 vectors now, and you could take your face. Okay, so this isn't your face. This is the author. This is Tim, good old Tim Chartier, or Chartier. I should have looked up how to spell it, or how to pronounce it. And you can ask, is Tim a linear combination of these 16 celebrities? So what is that asking? Well, that means that can you write the vector Tim as some scalar multiple of the vector, who was it? That's Audrey Hepburn, right? And Brad Pitt and Jackie Chan. C1 times the vector Brad Pitt. Okay, of course normally you should give your vectors one letter names, but it was actually Audrey Hepburn first. Plus C16. Can I name the 16th celebrity? Yeah, that's Tom Cruise, I think, right? Okay, and the answer is almost certainly not, right? Almost certainly not. Why? Because the span of these celebrities is a 16-dimensional, probably 16-dimensional subspace of R 540,000, and Tim here is just a vector in R 540,000, right? So the picture here is that it's the same. This is the only picture I'm going to draw for the entire quarter, right? This plane is the span of the celebrities' faces, right? So span of Audrey, Brad, ... This is a 16-dimensional subspace. This is R to the 540,000. And Tim is some vector here. So it's almost certainly Tim is not going to end up on this 16-dimensional subspace. But what you could do is you could project Tim down to this. You could project Tim down to this subspace. I should stop calling this vector Tim, but now I've gotten in the habit. And then you can solve for that, and that would give you approximately what coefficients you would need to put on these celebrities to get an approximation of Tim's face. Right? So in other words, what I want to do is I want to find the projection of Tim onto V, the span of the 16 celebrities' faces. Okay, and not only do I want to do this, Tim actually did it. So he got these coefficients. So, I mean, I guess you could say something like he looks the most like Brad Pitt and the least like Simon Cowell, maybe? That's not exactly what it's saying, but it does say that you should move the most in the Brad Pitt direction, right? And so you take these coefficients, and you can figure out what the approximate vector is by taking 0.342 times Brad, 0.329 times George Clooney, and adding them all up. And what you get is this image. This is the projection of Tim onto V. This is the best approximation of Tim's face as a linear combination of these 16 celebrity photos. Okay, and so you can go onto the Yale face database, according to Professor Thomas. You can Google this, and you can try this for yourself. Okay, and this sort of seems like a little bit of a just a joke in some sense, right? But first of all, it gives us another example where projection comes naturally because, again, we have another situation where almost certainly we have a non-solvable system, but instead we can project and solve. And it turns out that actual facial recognition is done in a way that's actually not so different from this. If you Google eigenfaces, which I think we'll talk about later in this course, it kind of is something like you figure out what you see a photo of a face and you figure out what coefficients it has, or you project onto some eigen faces, some subspace, and you figure out what coefficients it has, and that picks out features of the face. So even though this is kind of like a joke example, it's actually not so far away from like an actual practical example. There's no real practical example of doing this, what we just did, but hopefully it gives you just another example of a time when projection sort of naturally is something that you would want to do. Okay, so that was, I think, just a little bit of fun. Next time, I don't even remember what we're talking about next time. I've had too much fun preparing this lecture. All right, next time we're going to move on to symmetric matrices. See you then, more fun stuff coming.